Street Physics.
Hello and welcome to Short Chair Physics. Today in Short Chair Physics, we're going to be studying magnetism. Magnetism, you can do all kinds of cool stuff with magnetism. Like you can get something to follow your finger, like that. Look at that, follow your finger. Most people aren't fully aware that fingernails are actually magnetic, right? So we can get them to do that. We can train our magnet, right? We can train it. Let's see if I can train it to. Okay, flip over. Can you flip over? Can you flip? Oh, there we go. Oh, look at that. Ready? And could you flip over? Ready on three. 1, 2, 3. Oh, flipped over. And 1, 2, 3, and whoa, flip over and flip over the other way, and now 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 the other way, now the other way, now the other way, now the other way. See that? You can train a magnet to flip over, right? Very cool. You can also train a magnet to fetch, right? Hey, magnet, why don't you go get that alligator clip? Oh, I didn't tell you to flip over. That was pretty tricky. You did it on your own. Good job. Oh, there you go. All right, bring it over. All right. Got myself an alligator clip. Good job, Maggie. Right? All right. Now, magnets have been around for a long time. People have been aware of magnets for a long time. There was something called lodestones, which were they were just natural magnets. Not like these. These are neodymium magnets. These suckers are strong. Lodestones weren't quite as strong. They were natural magnets, just kind of like this. These are pretty strong too. These are ceramic magnets, people were aware that this phenomenon of magnetism existed. That stones would attract or repel. Certain types of stones would do that, and they didn't know why. And it wasn't until fairly recently, I think it was early 1800s or something like that. We had Oersted. Professor Oersted was doing a lecture. He was, I don't know if he taught something about electricity. I don't know what if he was a electrical guy, like an engineering or physics. I don't know. But anyways, probably a physicist. And he was doing a lecture on electricity, and he happened to have a compass like this. A compass, of course, is just a magnet and a bearing, and it's got a north and a south pole. Okay, so Oersted noticed that he had a wire near a compass, and he noticed when he sent current through the wire that the compass needle would move. That's pretty surprising. They had no idea at that point that magnetism was caused by moving charges. They didn't know that. It wasn't obvious there were any sort of moving charges in those rocks. But here it was. And what's interesting is if you take a look at this, so you can see the compass turns like that, and it's pointed that way when I put the wire over the compass. Watch what happens when I put the wire under the compass. So I put the wire under the compass, and it goes the other way. Let me put it on top of the compass again. Get the wire like that, and boom. When the current goes through, we could see that the compass needle turns. And watch what happens if I switch the direction. So if I switch the direction of the current, so we get the compass moves like that, and then if I switch, current is going in the other direction. You see the compass goes in the other direction. Like right now, the current is going this way. The current is coming out and going that way. And the compass kind of points towards me. Now, if I send the current, now the current is going this way, And you can see the compass points away from me. All right. So not only did he see that current caused magnetism, caused magnetic effects, but the direction of the current changed the direction of the magnetic effect. So that was a huge discovery, that magnetism is caused by moving charges, right? All magnetism is caused by moving charges. Now, it wasn't obvious. It's not obvious in our permanent magnets what the moving charges are. We know now that they are due to electron spin. He had no way of knowing that at the time. Magnetism is caused by moving charges. So, all right. So, what can be a magnet? Metals can be magnets, but not all metals are magnets. Some are. This is metal, but it's not a magnet. On the other hand, this screw that's connected to it is. Let me grab a stronger magnet. So this is not magnetic. It wouldn't get picked up, but this little screw thing in here is. So this is made out of a magnetic material. And it turns out the black portion is aluminum. Aluminum's not magnetic, doesn't have magnetic properties, at least doesn't have strong magnetic properties. And this center thing right here is, this screw must have iron in it. It's made out of some sort of steel. This probably is too, and it is, yes. This is also steel. So usually when something is magnetic, it's because it has iron in it. Not always, could have nickel or cobalt, but iron's the common one, and commonly the type of iron, it'd be steel, which is mostly iron. Here's a nail. Now, a nail is not necessarily a magnet. Here I'm trying to I got to touch on these paper clips, and those paper clips have iron in them for sure, steel. But we could see that the nail has steel in it, and I've attached two little magnets to it, and now the nail can pick up paper clips. Now, is the nail a magnet? Right? The nail was attracted to the magnet. Is the nail a magnet? Well, most people say, well, no, it's not a magnet. It's just stuck to a magnet. But it kind of looks like it is a magnet, right? And this nail is a magnet right now. It's a magnet. It's not a very strong one. And what would happen if I took this magnet off it? Oh, it's still a bit of a magnet, right? It's still a magnet. Look at that. What is happening here? Now, if I take this and throw it on the ground, right? Throw it on the ground again, smash it on the ground. Now it's not a magnet anymore. It's not a magnet anymore. Unless I put this magnet on it. Now it's a magnet again, right? And it's a pretty strong magnet right now. Look at that. I can flip that around, it stays on. And I pull that away, and it stays a magnet. Not a real strong one, right? But it's still a magnet. It's a magnet. Interesting. All right. So what's happening here is in the previous lesson, I talked about the magnetic domains. This is iron, and it's got these different sections of electron spin that are aligned, and they're in domains, normally randomly oriented. But when I put it in a magnetic field, by touching it to another magnet, it causes a magnetic field to go through this, and the domains start aligning more, like that. And even when I take the magnetic field away, the domains stay somewhat aligned. They're not aligned as well as they were before, but they still do. They are still a bit aligned, and you can see that it's still exhibiting magnetism. But it's weak. And all I got to do is thwack it on some stuff, smack it around a little bit, give it a good thwacking. All right. Okay. Doesn't look magnetic. Oh, it still is magnetic. Well, yeah, thwack it some more. Oh. All right. It's not magnetic anymore. Thwack the magnetism out of it. Right? Thwacked it out. No more magnetism on that. I took some wire, and it doesn't look like it, but this has insulation on it. This wire has insulation on it, and I wrapped it around this piece of hot glue. And if I put current through it, where did I put my batteries? I'll put it on a piece of paper, might make it easier to see. Staples are steel. Boom. Which is most steel, is mostly iron. Boop, ba, bum. Let's go. Let's take this and send in current through it, and no, not really enough to pick it up. But if we take a look here, here I have my compass, and my compass isn't going to be affected by this. If there's no current going through it, the compass isn't going to be affected by this little coil that I wound, because the wire is made out of copper. Copper is not magnetic, and hot glue is not magnetic. But watch what happens if I put current through this. Ready? Boom! See that? Look at that. Right? So I'm definitely got a magnetism going now. Like that. Right? Not a strong magnet. I can't pick up a paper clip or anything like that, but I certainly can make a compass turn. But watch what happens if I take a similar nail like I had before and wrap that around a wire, right? So, or wrap a wire around this nail like this and put a little current through the wire. So this is similar to what we had here. If you take a look, I have a similar number of turns of wire. But now, instead of a core of material that is not iron, I have iron in the middle, and you can see that I have a pretty good magnet now. I don't have a good contact here. Let me make better contact. The other end will be stronger too if I do this. Boom. Oh, don't have good contact. There we go. Right. So there we go. So we got a pretty strong magnet. It's able to pick up a paper clip and a staple. Got a paper clip and a staple. And let's see if I can pick up two paper. Oh, two. Oh. Can't quite pick up two paper clips. Oh, there we go. I got two paper clips. I got two paper clips and a staple. All right. Oh, I'm cheating. I'm kind of cheating because it looks like the staple's kind of hooked in there. But anyways, I take the current away and it locks down like this. Now, this is still magnetic. This is still going to be a bit magnetic. It's probably enough to pick up a staple. Let's see. No, it's not. It is not enough. Let's give it some more juice. Let's give it some more juice. Let's put 3 volts through it. I'm going to use my holders because I can't really hold all these wires. Can't tell if I have current going through it yet. Do I have a good connection? Yeah. All right. Yeah, so this is working. All right. Now I've taken the current away. By putting a current there, I sent a magnetic field through the nail, and the magnetic field due to the current plus the domains, and I still don't have. Oh yeah, and you can see some of the domains are still aligned. I'm able to pick up a paper clip, right? I mean, not a paper clip, a staple. Barely, but there you go. All right. So this is an important idea. All magnetism is caused by moving charges. Could be current in a wire, but anytime you have moving charges, you have magnetism. In the core of the Earth, we have moving charges due to what we think is the turning of our core, made out of iron, got a lot of iron in it and stuff like that. So that is not necessarily a current, but we do have moving charges, and that causes the magnetic field of the Earth. So for a homework assignment, why don't you see if you can figure out what does the magnetic field look like around a wire with current traveling through it. If we put current through the wire, we see that the compass and therefore the magnetic field above the wire looks like it's pointed in this direction above the wire and in this direction below the wire. And really it should be pointing at right angles from the wire. So above the wire, it's pointing this way, and below the wire, it's pointing that way. So what sort of geometry would give you behavior like that? Knowing that magnetic field lines always form closed loops, what would it look like? What would the magnetic field around a wire look like? All right, so we'll do that for a homework assignment.
It's true. Treasure.